Right. So thank you everyone for joining this month's First Friday's presentation. And we're very grateful for Adam Lipinski to step in on such short notice to do this presentation as Claudia has lost her voice. And he's going to talk about potassium nitrite and its effect on wood. And I know many violin makers have used this particular chemical in treating wood, bow makers, I think, as well. And so it'll be very interesting to hear what um, findings he's had as he's delved a little deeper into the what happens with this treatment on wood. Adam just recently graduated from violin making school, and he's made quite a few violins in such a short time. And Claudia says that he's also going to hopefully start a PhD in September. So that's wonderful. So Adam?
So hello everyone. My name is Adam Łapiński and I'm from Poland, Poznań, Poland. And as was said, I finished. Okay, maybe I just start with a presentation because I have everything over there. Just let me share my screen and let me know, please, if you see it. Yep.
Good.
Yeah,
Good.
great. So can I just hide my face from here? Okay, I'm gonna talk about potassium nitrate, the chemical that is used in violin-making. And before that, it's basically like a report of a research that I conducted with two researchers, Adam Mizera from Institute of Molecular Physics in Poznań and Professor Alina Duis from Białystok, University of Białystok. And
Wait a minute. Let me mute these people. Okay.
Okay.
Sorry about that.
Yeah, and Dr. Adam helped me with performing spectroscopical analysis of surface of wood treated with KNO2, and Professor Alina helped me with morphological studies. But yeah, there was a question: who am I actually? And I don't know if I can tell myself a violin maker, but I'm certainly a violin making graduate because I finished this year a violin making school in Poznań at the Academy of Music, Ignacy and Paderewski Academy of Music. And I've created a couple of violins and also two viola d'amores, but maybe it's not that important because I also always had a huge interest in science. And basically, out of my frustration on teachers that I had so many questions during construction of the violins that they couldn't answer, I just started a science club in a academy of music to have an opportunity, a place to perform my own research, and of course on a small scale, still as a student, but definitely I found some answer that came to my mind. And one of the questions that came to me was the potassium nitrate, because I was so frustrated that my teachers cannot tell me why. For example, sometimes when I put potassium nitrate, which is common in Polish school, the wood becomes more pink. Sometimes it's more salmony. Sometimes it's more orange. And I felt that I don't have control over it, and that frustrated me. And I just wanted to know what on a chemical level and maybe on a technical level is going on, and how I can control it. So on that beautiful KNO2 molecule will appear a lecture schedule. And first of all, I'm gonna talk about visual color changes of spruce and maple. So wood used in violin-making after application of nitric acid salt solution. So that will be just visual color changes without any deeper analysis. Then I will try to ask a question: how deeply does potassium nitrate penetrate the wood? Then I will talk a little bit about morphology of the spruce and maple surface, and the biggest one. So the spectral analysis of infrared spectra of spruce and maple wood treated with KNO2. Yes, and to be honest, I have to say it. I'm not a chemist. I'm not a physicist, and definitely I'm not a molecular physicist. And the whole research that I conducted was for me really difficult from that reason that I don't have a background in those areas, just high school knowledge. But still, I think that I come up with some interesting results, and I came up with some interesting explanations of those results that yeah, I want to show you. So first of all, I'm gonna talking about those visual changes between different chemicals, and I thought that the first thing that I want to try to find out is what part of potassium nitrate is reacting with food. Is it the nitrite thing, so NO2 or NO3, or the sodium part or potassium nite in the beginning? So basically, I've chosen 6 different substances that I've put it into water to have like different anions and cations, and then I brush it into the onto the board, and I created a special grid that you will see in a moment. But what is important, the visual changes were registered by. I'm not sure if it's a clever design, a clever idea to control that, but I used spruce wood and maple wood, and we all know that maple from different angles have different colors. So and when you lighten it up in a different way, it also changes color. So I come up with just a simple idea of using that kind of a page scanner that always have the same kind of a lighting process and the same kind of a scanning, so photographing process, to have similar results between every scan. So I prepared the chemicals. I put it into the UV lamp closet, and the lamps that I've used was the typical UVA used in Violin-making, and then I scanned the wood to have some results, and that's one of the first scans that I've done, and you can see a grid that have rows and columns, and you can see that I've registered changes in time periods like 3 hours, and you can clearly see differences in color that shows. But what's in which row? Yeah, and I did the same for maple. And in each column, there is a different percentage and a different layer of different number of layers, and in each row is different substances, because I also wanted to check the exact influence of a percentage of the solution, and how it applies to. So, for example, if I put 3 times 5% KNO2, it will be the same as 1 time 15%, which we'll discuss later. Yes, and then I came up with. I also was. That my teachers told me one thing, that I had to pre-treat my wood with UV, because if I not do that, the wood will come pinkish and not that good. So one side of the board was exposed to UV for 7 days, and the other was not. So I could see exactly what is the influence of UV pre-treatment. And because after grounding, there's always a varnish, so I've treated the plates in a normal way I would treat my violin. So I applied a ground layer of kaolin and oil varnish, which changed the color. I've applied 3 coats of and I applied varnish, and it was spirit varnish. So analysis. First of all, we can see that different substances have different influence on wood, and it clearly can be seen from that slide that the part of the chemical that is crucial to the reaction is NO2, so nitrate, and we can see that NO2 both in potassium and sodium nitrite reacted very similarly. But KNO3 haven't reacted that much, so probably there's a different reaction going on, or the same reaction but on a smaller level, not that intensively. We can also see that obviously spruce have reacted more profoundly than maple. Yeah. Okay. Grain of that. Yeah, because I wanted to know. Yeah, sorry, I lag. I wanted to know if the graying of NO3 is related only to UV exposure, or just to just that the substance had some effect. So here you can see that that it's not the case. Influence of the nitric acid salt solution on maple and spruce, and here you can see that with increasing number of both layers of applied substance and also the percentage of the solution, we have more profound color and more intense color, and both in maple and spruce. And the question that I had in the beginning, so 50% doesn't equal 3 times 5%. And we can see that the color is different, the intensity is different. And I personally prefer the look of 3 times 5%. So maybe it's better for overall saturation and equalness of the color on the instrument to put more layers, but of lower percentage. Yeah, and because I monitored how the color is changing through time, here we can see that the reaction duration is about 72 hours, and after that the color doesn't really change much more. And the greatest change in color is just after application, so until 6 hours the color changed a lot, and then just gradually those 3 days it changed color, and later it didn't. And I left the samples in a closet, not exposed to light, to sunlight, to just see if the color will change after a year. And you can see that the color is basically the same, and I personally cannot see a difference. Maybe yeah. And here are the changes between the pre-treated side and not pre-treated side, and you can see that there was some lignin oxidation, so that we can see the difference in color between the wood that is UV treated and UV not treated, obviously. And here's the influence of that on color. And to be honest, I don't see much of a difference. Like there's a little bit when I didn't use UV without UV pretreatment. It's true that the color is more red, but the difference wasn't that big that I thought that would be. Okay. So the second question was, how deeply does potassium nitrate penetrate wood and react? And to find out, the first slide is that we can see that between when the tape was, so I didn't apply the substance here. We still can see that potassium nitrate went into the wood fibers and penetrated the wood in spruce in a direction of grain, and in a maple mostly in a direction of flame. Oh, sorry, in spruce in a direction of grain, and in maple in a direction of flame, but gently. And also from this slide we can see that that UV is really important for the whole reaction to go on, because the spaces where the tape was put, where the light and the UV light didn't like lighten the surface, the reaction went more mildly. The color is less strong. Okay. Yeah, but that's in that right direction, and that is, but what about like how deeply really the surface goes into the surface, like how deeply the chemical goes into the surface? So not in that way, but deeply. And to do that, oh yeah, I've used that kind of a microscope that is used in hospitals when and you can see the results here, that spruce samples have had soaked a little bit more the substance, and the substance reacted till 0.4 millimeters around, and in maple 0.3 millimeters. Yeah, and the third question, so morphology of the spruce and maple surfaces after application of KNO2. And morphology is basically a study about the shape and texture of material surface. And it can be measured by scanning electron microscope, which is just, maybe not just, but that big tube is shooting electrons on an object, and the electron that maybe those technical stuff are not that important, so I will just go on. But you're probably familiar with the photos of scanning electron microscope that looks like that, and wood actually looks like that. So we clearly in the spectrum, in that kind of a magnitude, can see the trachate structure of wood, and on the right you can see how the wood is composed, and on the left on the picture we can see the trachetes very clearly. Oh yes, and that kind of a piece is a piece that I've cut it from the samples I made, and the samples look like that, and the piece is just that little corner that I've cut it. The thickness of the samples were 1 millimeter, and adjusted with a drum sander and finished with a scraper to just have clean look. I've used 10% solution of KNO2 for that morphology study, and all the samples were put into the UV cabinet for 85 hours, and it was the same UV cabinet with the same UV lamps. And what is essential in SEM imaging, that you have to put gold on the samples to prevent charge buildup. So I've also done that, and yeah, that's how the samples looks inside the SEM. And when SEM results, great. Ooh. So that's 100 times magnitude. And when we try to look closer, for example, 1000 magnitude, we can see the structure of wood very closely, that is composed of that's actually kind difficult to find a way to describe it, but when we go even more close, we can see that the structure of wood looks really interesting. And that's spruce wood, and in the middle we have maple wood, and on the right it's beech for 100 magnification from literature that I found. So basically, between species there are not that much of a difference in wood. So spruce looks very similar to maple in that direction, in that kind of a surface photo scan. And that's a photo with spruce after application of KNO2 after 2 hours in UV closet and after 84 hours in UV closet, because I wanted to check if there's any difference that UV light is like interacting with wood morphology. So basically that's how the clean spruce looks like, and that's how it looks like with KNO2. And we could clearly see that something changed, and it will be evident a little bit later here that we have something like a small lumps, small crystals on the surface, and it's evident here when you can clearly see that over there we have like a normal fiber, and everything else is just a potassium nitrite lump. Yeah, and before I will go into spectral analysis, if there are there any questions about what I've said so far?
I have a question. So just the act of putting water raises a grain. Does that change the morphology I mean, is that one of the differences you're seeing at a microscopic level?
It's a great question, and I haven't got an opportunity to check it. I've pre-created samples, but the SEM electron microscope, the electron gun had like something happened to the electron gun that I couldn't like check all my samples that I prepared. But I tried to find out an answer in literature, and I couldn't find some. But later on, when I will show you the spectral analysis, you will see that those structures that was shown in morphology are probably lumps and not just grain or trachate walls that come up.
Mm-hmm. And also the gold, is that at too fine a level to show up?
Oh, the gold is not is invisible in that kind of yeah. It's like a normal procedure to everything and to every SEM imaging.
Thank you.
Okay. And that's okay. So my idea of performing that spectral research method was to create a really thin stripe of wood, spruce and maple, that light would be able to go through, and then put some chemical on it, as you can see on the middle picture, and see what's the difference in spectra, in infrared. So here you can see that I've put the sample inside the spectrometer, and I've done multiple measurements over time to see if the change that is going on a chemical level in wood is going like linearly or not linearly. So I've done that many of measurements, and yeah. Yes, and I also wanted to check what's the spectrum in infrared of just potassium nitrate solution in water. So I've tested just normal water, then 5% potassium nitrate to dissolve in water until 15%. And the results, so here you can see the spectrum in infrared of solution of potassium nitrate in water, and over there, those two maximums are connected to asymmetric stretching vibration and symmetric stretching vibration of water. And maybe I could just tell it because analyzing spectra of light in infrared and substance in infrared is really similar to analyzing acoustic data, because spectroscopy is also called vibrational spectroscopy. So it tells us how the structure vibrates on a molecular level, how the molecule vibrates. And because all the bondings, all the atoms vibrate itself and rotate and spin, and that's something different, but also rotate and spin in according to each other in bonds. And that's ER spectroscopy. And also in that spectrum you can see here the maximum that is connected to scissor bending vibration of water. But here on the side, very little, we can see something really interesting that is truly and most obviously connected to nitrate vibration, nitrate anion vibration. And you can see that with an increase of percentage solution, the percentage of the nitrate in water, the intensity of each maximum was increased. And when you're analyzing ER spectra, you can talk about the position of the maximum, so the same like a frequency in acoustics, about the intensity, so how high is the maximum, and also about the width. And all those three properties of a maximum and changes in those three properties can mean different things. For example, intensity changes when there's more molecules that vibrate in the same way. So that's quite logical. But for example, the position of the band can change when, for example, the distance between that oxygen and nitrogen atom change. And also there's so many other stuff that can influence the position and the width that I'm not gonna go deeper into. But clearly we can see that in ER spectrum and of the solution of the KNO2, we can see vibrations of the NO2 anion. And here are the spectra, spectra of maple and spruce. And you can see that they are, quite complicated. And that's because wood is quite complicated. And basically what have to be done, I had to analyze literature to find out which band is connected to what kind of a vibration. So just a slide ago, I showed you that 1235 vibration maximum is connected to NO2 anion, and the same had to be done for every maximum on those wood spectra. And you can see it here. And it's not important to just go into, but maybe it will be essential in discussion later. And what's so difficult in analyzing wood is one single maximum, one single band could be connected to many different things. And for example, 1735 band is connected to hemicellulose, lignin, and actually cellulose and hemicellulose. And you can see on the right that some bands are visible in different kind of substances, and that complicates a lot identification of a reason why a band is growing or moving, because you can't really say which substance is changing. So so let's try analyze those spectra. And first region that I'm gonna analyze is that region from 1200s to till 1300s, and we can see that in orange we have a spectrum of spruce sample with KNO2 after 63 hours. In red is just normal wood, and in pink is wood with UV treatment, and similarly in maple. And what we can see is a big change between orange and red in a maximum region from around 1200s. And we can see on the top the intensity ratios, because wood is so anisotropic. So when you are comparing data and different measurements that were performed in different times, you have to have like a band that is definitely not changing to have something to compare and create a ratio, and then you can create an intensity ratio and show differences in time. So on top we can see that those 1200s bands grow really rapidly in the first 30 minutes, and then they are quite stable. They're raising a little bit. So as you remember from before, I've told you that the KNO2 solution and the NO2 vibrations were located around 1200s, and it looks really convincing that that what we can see here is actually those lumps. But I wasn't convinced that much, so I prepared something that is there's a technique of scanning solids also, spectroscopy with spectroscopy technique, and to make so you use potassium bromide with the substance that you want to measure, and basically you take potassium bromide, a lot of potassium bromide, 99%, and put a little bit of the substance that you want to measure, grind it together, and then you have like a little pastel in like a special pastel making device that you can put into a spectrometer and see the spectrum. And here's the spectrum of the solid and also a solution. And again, we even more clearly can see that there's something in red around 1200 till 1300 that we also see in the spectrum of the wood. What we also can see from the solid IR spectrum that wasn't visible in a solution is a maximum around 2500 and a maximum around 800. And I was interested if those peaks also showed up in the spectrum, and yeah, I'm talking about those two maximums. And you can see that, yep, they're showing up. So there's a huge possibility that some potassium that you put on a potassium nitrate that you put on a wood don't react and interact with wood chemically, but just after evaporation of water, it appears and crystallizes on top of the surface. And the same could be seen in maple, that maximum at 2500 and the maximum at 800. Yeah, so that's the first region that we analyzed, and the second region that have changed a lot is a region from 1500 till 1800. And yeah, that's the region that is not that easy to describe from the reason I told you a few minutes ago. But firstly, let's analyze the effect of UV, because it's really good. It's documented in the literature in a really good way. So we can see that in our samples, we can see a drop in 1508 band and a gradual linear rise of 1733. And those bands are connected to skeletal vibration in linen and CO stretching in hollocellulose, respectively. So maybe one thing about, because hollocellulose might be a not common term to you, but it's just a term to describe cellulose and hemicellulose as a whole. So CO stretching in every cellulose-like structures and cellulose-like molecules. And that kind of band intensity change.
1 second.
Yes? Hello? Oh, okay.
I think someone put their mic on, just ignore it.
Yeah, sure. And that band intensity change is well documented in literature, and we can see that linen exhibits sensitive interaction with UV light. That's the first thing, and it captures 80 to 85% of light. So absorption of hemicellulose and cellulose is negligible. And what actually happens to linen is something that is called photodegradation. So kind of a degradation caused by photo reactions, so light reaction, reaction with light. And that photodegradation process results in forming phenolic hydroperoxides. And maybe it sounds really chemical and not intuitive, but it's just a phenolic ring. So for example, glucose is just a phenolic ring with CO and COH bonds. So it's just like a base of cellulose and hemicellulose structures that is getting a hydroperoxide. And also the photodegradation creates free radicals, and free radicals are atoms that are really, they're causing a lot of instability in a system, and they can be okay, never mind. And also the result of photodegradation are carbonyl and carboxyl groups. So on the model you can see what is a carbonyl and what is a carboxyl group, and basically those groups goes into the structure of hollocellulose. And you probably see, or maybe, that both carbonyl, both carboxyl groups, and both phenolic hydroperoxides have those oxygen atoms that have been added to the molecule. And basically what is happening to linen is something called oxidation. And that oxidation, because why it's changing color, because that oxidation causes linen to demethoxylate or something like that. Sorry about it. Sorry about my English. I'm a little bit stressed. Okay, never mind. And that demethoxylation leads to yellowing and to the formation of quinone groups. And quinone groups, you can see, is just a phenolic ring. So ring that is made of 6 carbon atoms. With additional group, carbonyl or carboxyl group. And those quinone groups are responsible for that yellowing color that we can see after after applying UV to wood. Okay, and next part of that sentence on the bottom is that it also slightly depolymerized polysaccharides. So polysaccharides like cellulose and hemicelluloses are long chains of MERS, long chains of, for example, glucose, that are connected in a really long chain, and which is called polymer. And depolymerization just means cutting those really long chains into smaller pieces and forming similar groups and releasing gases like CO2, CO, and H2. When linen absorbs energy, its bonds break, creating new functional groups and radicals that further degrade and modify linen. And that's important because it's just like a process that is caused by UV, by giving additional energy to the system, but the whole process is how to say it, that it's moving faster and faster. Okay, never mind. But yes. Okay. Let's go forward. And that appearance of those quinone groups can be seen exactly at the band position 1734. And we can see that in spruce it linearly raised after 63 hours in a UV closet. And in maple we cannot see that kind of a big change, but probably because the time wasn't enough to show the change in maple. We can remember from before that maple didn't react that quickly as spruce, and that's also common for any biomaker. Okay. Okay. So that was the effect of UV. But what is the effect of the KNO2? And that's really hard to tell to begin with. But I will try, because I have a hypothesis. But I have to say that it's just a hypothesis made by not a chemist, and the whole research I want to publish. So I'm really happy that some reviewers will look into that and tell me if my hypothesis is good or not. But yeah, let's go with it. So we see a huge change in 1600 band and 1661. And according to the table that I've made at the beginning, it is connected to skeletal vibration in linen and CO stretching in hollocellulose. But it doesn't really make much sense, and because we are adding something new to the system, we are adding NO2, and I had an idea that maybe because in literature I could find informations that nitrocellulose monomer have a maximum at 1600s, around 1600s, that is connected to NO2 asymmetrical stretching. So maybe nitrocellulose is created in that process. And what could happen, in my opinion, and on the bottom you have like a cellulose molecule, cellulose two mers, and then you can see that UV light is kind of kicking the hydrogen out of the system, and in a place of a hydrogen, the nitrogen goes and connects to the structure, and that way it it creates nitrocellulose. So the hypothesis first, the number one hypothesis was that after cellulose nitration, stretching peak of hydroxyl groups on the glucose ring. So yeah. Oh yeah, that's sorry. Okay. Another thing about that kicking of hydrogen from a system is that we have to have some reaction in vibrational behavior, and that vibrational behavior can be seen by the change of 3500 maximum. And yeah, we can see that in place of those OH groups, when the NO2 groups into the hydrogen atom is going out, so there should be a change in the high end of IS spectrum. And there's the high end of IS spectrum. And yes, we can see that around 3500 there's a drop, and a sudden drop of intensity, and both in spruce and maple. Yeah, okay. Yeah, but there's a huge but, and the first but is that there are differences in those maximums that I've analyzed between spruce and maple, that 1661 maximum is going down in spruce and up in maple, so that's something that is a little bit interesting. But the second but is that, and it's a greater but, that in the literature there's literally no information about nitration with nitrate salts. So for example, KNO2. And when you type in Google Scholar nitration or nitrocellulose or nitration on cellulose, only nitration in concentrated acid comes like out of the browser, or some kind of a mix of nitric acid with something else. And at that point, I felt a little bit overwhelmed about the whole literature that I had to go through. And I didn't know exactly what to do next, but by probably a miracle, I found that thesis, that PhD thesis from 1987, that answers the question about if the nitration of cellulose is possible with nitrate salts, so for example KNO2. So first, from the thesis, we can read that there's a problem with nitrating cellulose with nitric acid alone, because the cellulose fibers like swell, and due to the gelatinization, it's hard for the acid to penetrate clearly and easily the cellulose. And what had been used sometimes was addition of salts, for example, potassium nitrate. And that's the that's the first thing that is interesting, that there's some potassium nitrate in the thesis. But what's more important, later on we can read that a wide variety of other nitrating mixes have been employed to nitrate cellulose to a very high DOS, and DOS is some kind of a number that indicates how many NO2 bonds have been created, because there could be like only one, only two, or only three in a nitrocellulose molecule. And what we can read here, that very high surface DOS can be achieved also by nitrating in a saturated solution of nitronium ion salts, so the thing that we are looking for. And to the artist's knowledge, this is the first time that nitration of cellulose with a nitrogen iron salt has been reported. So the question is, if it works, why is there's no literature about it? And the answer is that the nitration is limited to the very surface of the cellulose fiber. So it's really ineffective in an industrial way of creating nitrocellulose, because the reaction undergoes only in the top 30 angstroms or so. And to give you perspective, in that study, the nitrogen tetrafluoroborate was used. So basically a chemical that traps also NO2, NO2, and 30 angstroms is basically 10 molecules of water on top of each other. So it's really not much when you think about it. And we've seen that in spruce and maple, the reaction goes much deeper, because 0.3 millimeters around that. And that could be caused probably by the structure of wood itself, that is mainly composed of those tracheate pipes that have a lot of air inside. So it's more easy to for the solution to penetrate deeply, and the nitration can react. And over there you can see that the effect of the nitrogen ion concentration on the surface DOS achieved has been also investigated, and we can see that with increased solution concentration, also the DOS have increased. So the more NO2 bonds were created in a nitrocellulose. And that's something that also is connected to the previous, the first point of this lecture that I showed you before, that with increased concentration of those solutions, the color also was more profound. Yeah, and we can see from that graph that the reaction of that nitration is also really fast. It's just reacting in 45 minutes and then stopping. And that's something that we can see also in our graphs, that there was a reaction that bands moves really rapidly and then stayed at the same level. And those 45 minutes, for comparison, it's a lot in comparison to nutrition with mixed acid, like nitric acid with something else. So basically it was really inefficient to use potassium nitrate in creation of nitrocellulose. Yeah, but there's the first big problem is that the nitrocellulose is colorless, is white. So why there's a change in color, and that was really uncomfortable for me. That and the other but even greater is that nitrocellulose degrade under UV light. So if we will have nitrocellulose in the structure, it will degrade in time, and effect of those of the degradation is a photooxidation. So again, photodegradation is oxidation of cellulose, and it's connected to a formation of another products like lactone and anhydride functions, and that is something that is really difficult to explain. How to connect that hypothesis to real outcomes. So I had to think more. And also what's important, that during that photooxidation, the composition process, NO2 is released. So I've tried to find out what is really happening and tried other answers for that question. Yeah, and also over there you can see that I've listed the products of that photooxidation, so the products of the degradation of nitrocellulose and their appearance in ER spectra. So we can have, like, for example, glucanolactone at 1740 and so on and so on. And that's a problem because in literature we can read that UV irradiation leads to appearance of new absorption bands in hydroxyl region and in carbonyl region, and we don't have that kind of changes in spectra. So probably there's no nitrocellulose degradation going on. So there's probably no nitrocellulose also. So what could be the answer? To do that, I just measured and calculated an intensity ratio of every band, every single band that I had. And those are the intensity ratios that you can see. Oh, wow. Okay. And over here, you can see that I just try to search for literature for any, help and any answer that I could find. And I created a really simple kind of a way of showing what's happening. And those red circles indicate the bands that changed like the most drastically. So I should look on them in a first step. And so I put it all in a table for spruce, for maple, and I tried to find out different kind of changes in wood that could be similar to the changes that I've got in experimental data. So the first thing that I thought was maybe the cellulose is oxidating, and yeah, there is some change, but it doesn't fit into my changes. Maybe there is some cellulose nitration, and that's something that we were talking just a few seconds ago. And yeah, some bands are right, but some bands are wrong, and that's hard to explain. So maybe it's lignin oxidation, but nope, not really. The band that is connected to oxidation of lignin is 1735, and it should go up and not stay in the same position as at my experiment. So maybe it's lignin nitration, and that's connected to a lot of different peaks because lignin is really, really complicated. I will show it in a while. But no, any of those like fingerprint, like iconic, I don't know if I can say it, but any of those maximums that are characteristic for lignin nitration doesn't fit. Yeah, so maybe it's amidation or amination. So like when the NH2 atom goes into the structure. But no, it also didn't fit. So maybe, and you can quite start to feel my frustration at the moment. But then I thought maybe the other stuff, because wood is composed mainly from with cellulose, it's like 50%, hemicellulose and lignin, and there are like 5% of extractive substances that also are in wood. So I tried to look there, and I had some luthiers that told me that maybe tannins could be involved, but there's a huge problem with tannins, that there are like 4,000 different tannin structures. So analyzing it would be like really difficult and even I think impossible. And even individual species, the tannin suite is different. So that's just impossible to do. But apparently what I found, that there's even no tannin in spruce and maple wood. Like, of course, there's some in bog, and you can see the data that in Norway spruce there's up to 15% tannin in bog, but in wood there's nothing at all. Like harness, according to harness, it's 0.01%, and scalpwood is 0. And I tried also Douglas fir tree, that is also kind of a, yeah, and there's also a really low amount of tannin inside. And the same is in maple. Rowe said that tannins apparently are not present in maple wood at all. And there's a little bit of tannins in bog, like in black maple 1.9%, red maple 6.9%, but not inside. And even though, yeah, you guessed that, the maximums also don't fit. So that's tannins, probably there's not also tannins. The tannins are probably not also involved. Yeah, so I tried more, and I really tried to find any information of wood, of spectrum of spruce and maple changes, and what it was connected to, what kind of a reaction. And I checked the acetylization of hemicelluloses, esterification. I've checked the amount of free acid groups at different MLF. Okay, you can see how many things I've checked, and the only thing that fits my experimental data is degradation of the polysaccharides, but it doesn't really help a lot, because I know that there's some degradation because of the UV light that I'm using. So at that point, I was pretty, I don't know how to put that. Yeah, frustrated is a wrong word, but I couldn't find a solution, and but I didn't want to give up, and I just tried to go back in what I know, and I realized that like a month before I write it down, that during primary photooxidation of nitrocellulose, the NO2 is released, so in a gas form. And I came up with something interesting in literature, and I, like around 2 a.m. or 3 a.m. I contacted the doctor that I was working with such a message that maybe yeah, I'll just read it. Nitrocellulose degrades in a rather specific way. Initially, the ON bonds in the ONO2 group breaks, releasing NO2. In the presence of water or humidity, NO2s hydrolyze into nitric acid, which accelerates the degradation process, and which further release NO2, and that creates a self-sustaining cycle. To slow down this degradation, the industry used stabilizers such as aromatic amines or urea derivatives, which capture NO2 before it turns into HNO2. Unfortunately, the products of such nitration are not very environmentally friendly. However, I came across information about so-called green stabilizers, substances like curcumin and, interestingly, guaiacol, a phenol that is one of the main components of linen. And you can see on the right how the guaiacol is looking. It's the picture on the top, and on the bottom we have a nitro guaiacol molecule. And what is interesting, that guaiacol absorbs only UV light, but nitro guaiacol absorbs UV light and visible radiation. And visible radiation around purple, blue, green kind of a range. So it causes the, how to say it, guaiacol is white and nitroguaiacol is yellow to red to brown. So basically, thinking logically, increasing amount of nitroguaiacol modules should create browning and getting those colors that we are looking for. So what I've done, you can see maybe I'm going a little bit too fast, but In that study, kinetics and product in the identification of what is of nitroguaiacyl photolysis and under artificial sunlight, we can see that in literature and in my experimental data, we can see that in a visible range of light, we have a little bump here from 400 to 600, and that's common to maple, and it's the same in spruce. And also we can see that the amount of that bump is higher with the time that is so, and it's very logical, because we all know that I've showed before that with time the color of wood becomes more intense. So that's basically a representation of how it looks in a spectrometer data about that is and yes. So in another study we have another data that the main product of guaiacyl photonitration are that kind of maybe it's not important, but those phenolic structures that have NO2 components in it. After 3 hours under UV's irradiation, the photonitration of guaiacyl in the presence of yielded a yellow-colored reaction solution. So basically, after photonitration of guaiacyl, so after applying light and after applying sodium nitrite with H2O hydrogen peroxide, the solution becomes yellow. And nitroguaiacyl strongly absorb light in the UV and the yellow visible region. So maybe it's not important why it's the absorption bands in the spectra mainly results that is not important, but I'll go further, because the question is, if there is a photonitration of guaiacyl in the linen parts of wood, why the nutrition of linen that is in literature doesn't compare and doesn't match my experimental results? And that's probably because those nitroguaiacyls also photodegrade under UV light and under in nitrate mediated conditions. So that publication by Yang shows that those nitroguaiacyl models with UV light and with like an environment full of nitrite anions goes into different molecules, different chemicals, that just makes the whole system really unpredictable. And the linen, that's what I'm talking, that maybe that unpredictability that we see here in those three peaks, 1546, and we also have something like 1600, so it's 15 centimeters just off. It's not that far away, actually. The second peak, between 1300 till 1700, we have something around 1200s. So maybe it's also like a little shifted because the complexity of the system. So when you look at linen, it's quite a complicated substance, and it's not a whole of that. It's much bigger and it's irregular. So that representation that you see is just one representation that so there's maybe not infinite amount of representations of linen, but that one is just only one. So it's really hard to tell how complicated is linen. But it's built with three main building parts. It's a coniferal alcohol, coumaryl alcohol, and uronic acid. And in that coniferal alcohol, you can see a phenolic ring with CH3O. So that's our guaiacyl. So here can see a cumaryl that is in blue, and coniferal that is in purple, and one could assume that NO2 goes into the Guajacol ring like that, and with increasing amount of NO2 molecules, those bands increase. And that's basically what I thought about it. I also have a program that that shows theoretical calculations and theoretical vibrations that will enable you to see how the whole that particular linen interpretation vibrates. And it's true that for the coniferal alcohol, so that really small unit, when we add NO2 in it, it vibrates exactly in that 1600 region. But when we have the whole linen, it's undetectable really, and it's really hard to tell. And I will show you in a moment. But yeah, actually, I can show you now if you give me a moment. Okay, can you see my screen?
Mhm.
Okay, great. So let me open the Guajacol with just one NO2 atom, and it looks like that. That's the molecule. And that's really similar to model analysis. We have modes with frequency, and we can pick our 1600 mode and play the vibrations. I don't know if you see it, but definitely there's some motion in NO2. And it's really close to, wait. To 1600 reason that was that visible. The change was that visible, and the same. Oh, it's lagging a little bit. Sorry. The same is true for nitroguajacol that has two NO2 modules, and when we go into here, there's again a vibration for one and other NO2 atoms. But it's complicated when I open the linen. And that's the module that represents how the linen looks like. And that part of linen looks like that I showed you before in a sketch. And when I go into results in those 1600 region, okay, there's no more, like there's some vibration of the whole structure, but it becomes so it's just a little bit too complicated, and it doesn't really shows up. So to sum up, the idea what I have, what's happening, I think that that there could be a multiple reactions going one after another. Because when I go once more here, oh no. Sorry. Okay. So I think that there could be two reactions. The first one that is rapid, and you can see it in the first band, the second band, and also the last one. Maybe I will show you that in spruce. Okay. That is the first reaction that is rapid and is connected to nitration of cellulose, surface nitration of cellulose, that undergoes photodegradation, that releases NO2 in a gas form, that is catched by Guajatsol's parts of linen, that degrades under UV and creates something else. That, but we know that Guajacol also have those visible light properties of. I'm sorry, you see that it's quite complicated even to think about it, but that's my thesis that might happening. So multiple reactions one after another, and that's probably why nobody to that point hadn't published about it anything. So to sum up, stuff that we know, because it's better to finish with something that we are sure. The anionic compound NO2 is responsible for the brown color of spruce and maple after application of KNO2. So the anionic NO2, not K, not Na, not NO3. Nitric acid salts contribute to the darkening of wood, which is not only due to the UV exposure. So when you use NO3, it also will react in some way that I didn't spectroscopically look into, but there is some reaction not only connected to UV exposure to light. When applying a solution of higher concentration or a greater number of times, the intensity of the final color increases. Applying a 15% solution once doesn't have the same effect as applying 5% 3 times. The reaction is rapid for the first few hours after application and then slows down. So it's essential for violin makers to put the KNO2 if they want to, and leave the instruments for at minimum 72 hours to see the final result. Yes. Wood surface to which NO2 and spirit varnish has been applied doesn't change color after a year in a closet, and that's something that is optimistic. That the color we have when we are finishing our instruments won't change at least after 1 year. The 7 days long pre-UV exposure makes the color obtained after nitrate application more red, but I actually didn't said that, but after application of varnish, the difference between the pre-exposure and no pre-exposure was really small, and yeah. Nitrate soaks in strongly along the grain in spruce and gently in the direction of the flame in maple. So probably when we are applying the KNO2 and we leave a spot, there's a possibility that a little bit of that will soak in. And nitrate soaks in and reacts to a depth of about 0.4 millimeter in spruce inside and 0.3 millimeter in maple. The maple tracheate walls are not significantly different from those in spruce. After application of KNO2, the salt coated the wood tissue, forming clumped lumps that are also seen in spectroscopy analysis. After application of KNO2, a chemical reaction takes place, affecting the appearance of the maple and spruce wood spectra. After KNO2 application, those two bands increase significantly, and those are things that we know. Why they are increasing, I proposed a hypothesis, but it wasn't faced with reviewers I feel that that thesis needs a review. Yeah, and that's all that I have. So if you have any questions, that's the time.
All right. Thank you, Adam. So if you have any questions, if you can, try to use the raise hands function, which is under the react icon at the bottom of your Zoom app, or type a question into the chat. Okay. I want to start with a basic question before we get into the details of this research. And this is a question from Leo, but it's relevant to all of us non-violin makers, which is, so why do makers use nitrite treatment? If the penetration is only 0.3 to 0.4 millimeters, that is only 10%, 5 to 10% of the plate thickness. The treatment would likely have negligible effect on acoustic properties of the plate. And if using for color, couldn't the desired color be handled through various grounds or varnish? Let's just start that with a very simple, basic questions for us non-violin makers.
Yeah, so from my experience, I feel that the chemical treatment of wood is much more, creates a surface that is much more even in color, because when the arching is basically, the fibers in the arching are cut, so when you apply a dye, there's a possibility that you will have like darker spots because the wood is uneven and soaks dye unevenly. And when treating chemically, you avoid that. And when you apply the same percentage, like the same percentage and the same solution on the whole violin, it should have the same color.
Okay, Joseph?
Yes, well, thank you, Adam, for your work. I understand so little of the chemistry, so I just want to ask one question. You use the term nitration. What does that mean?
So maybe it's not the correct word, but it means adding nitrate anions to a molecule. So basically, cellulose nitration would be chemical change from cellulose into nitrocellulose by adding NO2 atoms, NO2 like molecules.
And NO, which is nitrogen plus oxygen, is a nitrate?
Well, wait a minute, Adam, can you clarify this? Because this is a little confusing, because technically a nitrite, so you've been, this is a subtle pronunciation in English. A nitrite is NO2. A nitrate is NO3.
Yeah,
and those
you're right.
have
You're
very
right.
different properties. And I noticed in that PhD thesis you found, they were talking about nitrates, not nitrites. So just want to point that out.
Yeah. Okay. Thank you for correcting me. Yeah.
Jim? You're muted.
Am I audible now?
Yep.
Okay. Yeah. Well, thank you for this. This is the best information on this subject that I've ever heard. Many years ago, I had a chance to talk quite a bit about lignin with Oliver Rogers, who was a pioneer violin acoustics studier, and Oliver also spent some time in the paper-making industry. So he knew quite a bit about lignin, because for the paper makers, that lignin is just a big problem, something they want to get rid of. But lignin is a very complicated molecule, as you've said, which changes its properties with heat and with time. If you view wood as a bundle of cellulose straws bound together by lignin and with some hemicellulose in there, which is but let's ignore the hemicellulose for a while. Lignin in fresh cut wood is a thermoplastic material. It softens with heat. But when you do heat it, it becomes more of a thermoset material, which is why fresh cut wood is much easier to bend than and if you're bending a piece of wood, the best chance you have to do it is the first time. Once you've heated it and bent it, you'll find it very difficult to unbend it, because it has transitioned. Anyway, what I'm wondering is, in your studies, have you observed any changes to the property of lignin brought about by the potassium nitrite?
I haven't monitored temperature inside the UV cabinet, and so that's something that should be also measured in the future, for sure. Although all the samples were in the same lamp of the same volume of air, so probably the temperature was similar, and the cabinet was closed. That's important. So with ventilation, but it was closed. Yeah.
I do think that the way that lignin changes over time is an important factor in how violins change as they age.
Jim, is that visually and or acoustically?
Acoustically, I'm thinking about.
Okay.
I don't have a way of knowing, although, one of the things that we observe is old wood is naturally yellow, and the older it is, the more it has that yellowish color that we love. And the yellowish color eventually goes a little bit deeper, but it never goes all the way through. But still, if there are changes in the mechanical properties of the wood, even if it's only at the surface, well, the surface is the most important part in terms of bending stiffness. So I'm just, anything we can learn about that is an important thing to know.
I have some answer for this question, but I have to look for it.
Fan, I can't raise my electronic hand. I'm
Okay.
raising my field.
Okay, wait a minute. We're gonna cue you up. Okay. So
Okay.
um
Okay.
let's go to the next chat question, and then I'll come to you, Alcus. So Catherine asks, was the long UV pretreatment done dry or wet? If dry, do you think wet UV treatment might be better?
What do you mean by wet or dry UV pretreatment? Like the wood was
I
wet?
assume she means, yeah, whether the wood was.
So it was dry wood, put it into a UV cabinet and left for 7 days and monitored each day twice. So I have data from 12 hours around how the wood is changing. But it was wet.
I meant it would be immersed in water, so it would be really wet, and that would change the surface, might swell up, make things easier to diffuse into the wood.
So I'm not sure if it's applicable for violin wood and violin corpuses. And I haven't thought about it, and I don't know the answer, but it's really curious.
Okay.
Okay, Alcus.
Okay.
If I could just show you one thing about the question that was a second ago. Do you still see my screen?
Yes.
Oh, okay, great. So here you can see that The crystalline, the second dot. The crystalline structure of cellulose in 300, 400 years old wood doesn't differ from fresh unaged wood. However, the degree of condensation of linen and the number of polyconjugated systems increases as a result of oxidation, and the amount of acid-soluble linen decrease. So there's a decrease in linen content, so there's decrease in density. Linen exhibits natural aging corresponds with the decrease in density of those bands that are connected to linen oxidation. So basically, natural aging also means oxidation of linen, and cutting the linen, the scission, and I don't know if it answers your question. It's definitely could have potentially an acoustical influence just by the density difference.
All right, so let's go to Alkis.
First of all, congratulations and thank you for a great piece of work. Very interesting, educational too. So congratulations. Keep doing it. Now I have a couple of comments. And also I have to mention that I had problems with the internet, so I was on and off. It kept dumping me out, so maybe I missed already something. Going to the very beginning of designing the test, you showed you are trying to find out the influence of cationic species, if there is an effect by the cationic species. I would have done something a little different in presenting the concentrations that you use. I would have done the concentrations on a molar basis, not on percent weight, because obviously there is a great the active species is, as we know, is the nitrite part of the molecule. So I would have done that basically on molecular concentration, the study. The other thing that I would have liked to know, or have done it, is to monitor or at least keep a track on the pH. pH, in my understanding, has a very great deal of effect on a number of reactions, quite a number of complex reactions in the wood, and also includes the color effects. So, for instance, if you do nitrites application, just experimentally, and you get a color on it, if you wash the surface after that with, let's say, acetic acid, vinegar, you're going to see already a color change. If you, after the treatment, you're going to apply ammonia, which you convert the other way around, go alkaline, you're going to see again a different color change. So it would have been interesting, or at least for the next time the work is done, to actually have the pH as either a variable or a fixed value. Another comment that I would make is from my understanding from the work and whatever I know from before, is it is actually a very good thing that the nitric acid, nitrites, do not really penetrate too much into the wood. If they did, I believe that they will eventually destroy the physical properties of the wood that we rely on when we make violins. So probably it will be a good idea that it's only a surface and only to consider for color effects, or maybe as Jim Ham mentioned, the surface importance as well, the stiffness of the surface itself. The other thing that it would be nice to know would be if any of these treatments, let's talk about nitrites, changes the relative longitudinal versus transverse stiffness of the wood. When we carve based on tradition, the wood, we rely on a certain range of the stiffness transverse versus longitudinal into the wood. If we do any treatment that drastically changes that, for instance, to exaggerate, if you change the transverse stiffness to be equal to the longitudinal, I might as well do the whole thing in plastic, not a piece of wood. Or you have to change drastically the way we arch and the way we graduate. But anyway, the whole thing is extremely complex. The chemistry is very complex. And thank you again, and congratulations for a very good piece of work in a complex type of system. Thank you, Adam.
Thank you very much.
Okay. Thank you, August. Jim?
Yeah, I have a second question regarding the ultraviolet light. My light box is many years old now, and the fluorescent bulbs are tired in it, and it doesn't work as well as it used to. And I understand that there are now LED alternatives to using fluorescent ultraviolet lights. I'm wondering what lights you're using in your light box.
So I've showed in the beginning, in that light box, it's that lamp Actinic BLTLTLD Philips with a
okay, so those yeah, so BL yeah, that looks like the fluorescence that I'm used to, not LED ones. Okay.
Yeah, I know that, for example, the degradation of nitrocellulose is also the ratio, not the ratio, the time which is required for the nitrocellulose to degrade is connected to the UV frequency. So UVC can degrade in like I don't remember, but much faster than UVA. Yeah.
Okay, are you done, Jim?
Yeah.
Okay. Joseph.
I have it might be good to put some perspective on the history of using these things. Did you research that? When did people first start using these kind of substances? I know something of the recent decades, and I can comment on that, but have you looked into earlier use?
I tried because I wanted to find out who was the first one who thought that, you know, additive to food could be used in violin making. It was really curious for me, and I couldn't find any information online. I asked my teacher; they also didn't know. One of them told me that that it was like proposed in Paris, but he couldn't really tell much more. So I didn't know that.
So I read in there is a book on varnish. I can't remember the names, a German scientist, and then a German maker, Stefan Greiner. And I think someone can please correct me. I think they found some suggestion that there were metal salts on the wood. Would that be would that go along with the sort of treatment you're doing?
So the problem with historical chemical treatment is that there's a lot of information about, for example, okay, how to say it? It's iron with FeSO4. So yeah, I'm really bad in those chemical names like nitrate. Sorry for that. Yeah, the chemical used for dyeing purfling or yeah. And there's a lot of information about how in ancient, maybe not in ancient times, but in olden times, they get that chemical from rusty nails, and so there are salts, metallic salts also, and it's hard to tell from that information to which salts they are, you know, referring to.
Okay, so when I started in violin making in the late 1970s, and there wasn't much information around really, I kind of vaguely heard about using nitrates, potassium, these things, permanganates, to stain wood, and being warned against them because they might destroy the wood and turn green later. So there's a good deal of suspicion and not a lot of information. I think it changed a lot. Oh, for myself, tanning the wood using UV was early. I adopted that early, and found that if you then fumed at pneumonia after tanning, that did produce quite a pronounced yellowing, and that's probably related to some of the things you're talking about. And then maybe was it in the turn of the century that Ken Padding did his work, and he came up with was it imprimatur jurata, which I think was analyzed, and I got a formula for making it, which contained, let me see, 5% nitrite, potassium nitrite, approximately, and approximately 0.45% nitrate, and about 0.06% potassium chloride, and then there's some ethanol, and the rest is water. Does anyone know, maybe Alkis or Adam, what this particular formulation, does it have any advantages? Should we care?
You're asking me? Okay.
Or Adam, whoever.
Soon after Padding came up with the formulation, I had it analyzed at that time, and I found approximately the concentration you're talking about. They had the nitrites and nitrates. I didn't publicize the analysis because as long as he was alive, congratulations to him. It was his right to use it, so I didn't talk about it.
Mm-hmm.
But the active species, both, I think Adam also showed that at the beginning, that both nitrite and nitrate, they have some effect on the wood, but it's different. And also their effect is different on different pHs. In the case of the Padding's formulation with nitrites, the pH was kept in a safe range for the wood itself, which was around around 8 pH 8 or something like that, which it's pretty safe. So there was a little mostly nitrite and some nitrate. Now, when you buy chemicals, usually you will find a conversion from one to another, and you have some sort of an equilibrium. So you are going to find some nitrite, some nitrate. In the case of whatever Padding was talking about, he said he was extracting these nitrites from natural sources as opposed to chemicals, for, reagents. So in that case, it's possible that you have both nitrite and nitrates. If you look at the chemistry of nitrogen, nitrites, nitric acid, nitrites, it's extremely complicated, and the species from one to another, you can get nitrogen, you can get, just to give an example, when we first started looking at the oxidation by this oxide, I remember Bill Fulton, he had electrical discharge, plasma, Tesla coil, producing nitrous and nitric oxides in the presence of humidity. You're coloring the wood, which basically is the reaction of nitric acid, not salts, nitric acid. That was pretty destructive to the wood. You get colors, but you get also destruction of the wood. So the active species were the fact that in the Padding you found some chloride and some other stuff. Those do, in my opinion, they don't do anything. They are just there. When I analyzed, I found them because he was using natural compounds. The same thing with alcohol, that he was using some limonene that I found there. Well, apparently it was the alcohol he was using was some natural type of, I don't know, maybe from wine or from some lemon something. So those things, I don't think they do anything. The other thing he did later on, he introduced some dye into his composition because people were complaining at that time that when you apply it, it's like water. You can't see where you applied it. So he added later on a little dye, which is not a bad idea.
And that dye, the dye faded. It was a fugitive dye. only there as a kind of a tracer. I
Whether
think.
or not, it really doesn't particularly matter, in my opinion. But anyway, you're not relying on that. Later on, I'm just also mentioning that you can make this composition, you can put some dye into it. However, if you have an oxidant and you have an organic compound like a dye, there's going to be a reaction between those two components before you even apply on the wood. So you look at, you add the dye there, and you have a moving target. You don't really know how much the concentration of the active species is. That's why also these solutions, you keep them in the sun, and they tell you, well, they have a shelf life of, I don't know, a year or something. After that, they degrade. So it's very complex. And if you just look at the chemistry conversion of nitric acid, nitrogen, from one oxide to the other, it's quite complicated. Now, when you apply it to the wood and you don't keep the pH as a control variable, you are asking for additional complications. In other words, you can't define all the parameters when you control that type of study unless you actually control the pH. The other comment I will make, if I may, that, well, the humidity needs to be, when you do study over time and you monitor things, the humidity has to be more or less controlled. And I think Adam mentioned that he has some control on the humidity. The temperature will affect the reaction, the rate of reactions. So when you apply something like nitric acid or anything else, the temperature itself has an effect, which is well known in chemistry, on the rate of reaction. So if you are going to monitor things over time, well, the temperature is also a parameter you need to control. Otherwise, you're going to get colors that change in time. And, well, they're not quantitative. So that whole thing is very, very common. Then you have the penetration, as we said, you only go about 0.3 millimeters in one, 0.2 on the other samples. And that will give you just a serve. And then you apply multiple layers of a solution, the water evaporates. So in effect, what you've done, you get eventually saturation with crystals. As I think Adam already mentioned, after a number of applications, you can get the salt coming off. So you look at the microscope, you're gonna see the pores of the wood flooded with some solid that it's unstable. That solid is basically still a nitrite, which will continue reacting in time, maybe 200 years, whatever. With a change of humidity, changes in temperature, changes of that salt is unstable. Ideally, I would very much like, and I'm doing certain things myself, to try not to use the nitrites anymore. I've been through the phase of using nitrites for a very long time, like everybody else. And recently, for the number of years, at least on the maple, I don't need the nitrite. Now on the spruce, I still use the nitrites, not because I want to get the overall color, but I think Adam's work confirms that it does something to the longitudinal type, to the grain. You can actually probably see a little more reaction to the winter grain, for instance, okay? Maybe if the lignin part of it. If you do some color change there, maybe that's useful. But actually, and if you want to do a treatment for, in my opinion, for the other treatments that people have talked for the acoustical properties of the wood, well, those treatments will require a penetration. It will require, you cannot count on a penetration of the piece of wood, of logo that comes down on rivers from the mountains. People had all sorts of speculation for because penetration of that could take 200 years. I don't think Stroud or anybody else was counting on 200 years of a log coming down the river in salt water or some other water. So there have been studies that have found all sorts of metals are naturally more in the Cremonese, let's say Stradivari Guarnieri, which is versus a blank from the same type of, from the same period of time. And they found there is enrichment in certain metals. well, that might imply some sort of application. But if that happens, in my opinion, it has to happen on a thin piece of wood. Otherwise, you can't wait for a long penetration. And you cannot apply any of these drastic treatments on wood. If you already put glue on it, you glue the joint, you can't actually soak it in anything. Or if you glue the purfling, you can't soak a thin piece of wood in water. So people, well, these are some, anyway, I wish I had another 50 years of life to think about this thing and work on this thing, because the subject has been studied in modern times for a very long time, since the beginning when I started 40-something years ago. It has been studied, and there is still no direct answer. The one thing is, Adam's results were very interesting, including the nitrocellulose. I looked into that briefly, and well, of course, he's right, doesn't do much to that color thing. The color comes from elsewhere, not the nitrocellulose. And besides, it's nice that we can't, it is actually a good thing we cannot convert everything to nitrocellulose, because then you could catch fire, blow up.
Yeah,
when you make
explode.
exposure.
So
By the way, Adam, just as a background, Alkas has led a dual career, both as a research chemist and as a violin maker.
No, it's so like.
Which makes it very complicated, believe me.
Yes, indeed. And the topic is even really, really complicated from a spectroscopic point of view. So like a a SPAT that is working in spectroscopy, wood is like a top anisotropic.
Well, that is that's complicated. I haven't looked into that, and your work is very interesting. Now, what I do with it, I don't know. But
so I know that probably those that idea that came to me that, oh, I'm just curious what's happening chemically, could be really weird, like hard to use, not useful. Oh yeah, that's the word. But I just tried to understand how it works, to maybe come up with new ideas using similar patterns, similar reactions to get different colors, different results, to just broaden the scope of tools, of possibilities, of things that you can use to color and dye a wood. And I actually found two new substances, and I can share it with you. They are not healthy to eat, and probably you have to be very careful. And I don't. Yeah, it's just do it with your own safety. But give me 1 minute. One was pyrocatechol, and the other phenyladenamine. And those substances are like phenolic structures that could be used to. Yeah, I'll just show you.
You mean you apply them on the wood?
Yep. So
okay, if you do that, wouldn't you have the same type of issue that you have with uneven penetration, like with the dyes?
So, oh yeah, those two chemicals react chemically and change chemically the structure of wood, and they are also used in the linen industry, in the paper making industry, to see if there's any linen left in the pulp. And
that approach is of interest to me, because what I'm doing with some other people, it's by analogy to the textile industry, that you can put a mordant and you can put a dye and you can do that, you can do this. That is of interest, and I'm doing something of that in my work. We're working with mordants and the dye and stuff like that, instead trying to avoid going with the nitrites. Other than the top, that now I use it, now I don't. It depends how I feel. That's of interest. But okay, from my own experience, Fantauer said I had a schizophrenic life. I was parallel full-time for the last 40-something years, both engineering, chemical engineering, doing research, which is very nice to know everything. and then of course making violin making. But there is a point that if I try to do, I didn't want to get into the violin making to do research, because that was my career. I've done research, plenty of it. That's what I've done in my chemical engineering work. I didn't want to spend my time to do that, but I do appreciate when other people do the research, they put in the time. That goes for the acoustics people too. I really appreciate that they do that for me to be, and especially when they share it. So for me to actually digest it, to look at it, to pick from there what fits in my work and use it. But if you're trying to understand everything in a complex thing like wood, both acoustics and coloration, you have to decide how many violins you want to make in your lifetime. Because you're going to have to, something will have to give.
I'm not sure if that's common for every violin maker, but with every violin that I make, I'm not really happy, and I know that there's something that I could do better. So I don't want to build enormous amount of violin, just one that satisfies me. And I hope that acoustic and chemical research will guide me into the direction of create something that satisfies.
But I like what I hear, because in my case, that was it. I wasn't planning to make, I didn't want to make many violins. I didn't have to make many violins. I wanted to make the best I can, both acoustically and visually. So to do whatever it takes to get to that point. In the same time, of course, I had to work with some other job too, so I can make all these things possible. Anyway, it's very good work. I hope you continue. I hope you interact. You can share your work with us. And well, hopefully you can get some good ideas out of these things.
Thank you for your words, Alkas. Joseph.
Yes, this is all so interesting. So I think it's worth putting out there that, I mean, from a maker's point of view, from my point of view, these solutions have been fantastically useful in, at least for my making varnishing process. They're inexpensive. You save a lot of power by not running your UV for weeks at a time. I just do it for hours, enough to cure. The only downside practically is that they raise the grain of the wood, so that you've then got to rescrape or do it several times before you use them. Otherwise, my only concern is what Alkas touched upon. If you take a simple solution of potassium, would it be nitrite, is that dangerously, is the pH dangerous in any way? Is one question. And the second one, can you simply rinse off the wood afterwards to get rid of any residual crystals?
Well, if you do that, then you raise the grain. I mean,
well, the grain's already raised. That's history. It won't keep raising. It'll eventually, you scrape it and nothing happens.
So for violin makers, I have another observation to make.
But could you answer that first? Is it is it dangerously
dangerous to leave it in?
You said the pH-D, if it's wrong, it can be dangerous to the wood.
What is dangerous to the wood is nitric acid. But nitric acid at a certain concentration is a very strong acid.
I understand.
They say that because that destroys the wood itself, has nothing to do with the coloration, is the pH of it, which is the same thing with the sulfuric acid and the same thing with the hydrochloric acid. If you use any of that you're going to destroy the hemicellulose, you're going to destroy the cellulose eventually. They hydrolyze, they decompose, and they give you acetic acid and formic acid and stuff like that. Okay, which means you alter the wood properties that we're used to deal with.
Yes, okay. But Alkas, is potassium nitrite, does it have that effect? I understand that.
But the potassium nitrite, the beauty of applying it as a solution, which as far as I know, well, I attribute that to Pat Gooding, that's padding, is that he made a solution that you have a control on the pH, so you don't go very acid, it's not pH 0, is not, it's a pH 8, which is, well, water is 7, is safe, okay? And you have that, so you don't have that type of reaction of the cellulose, hemicellulose attributed to the acidic environment, never mind the color, never mind the oxidation, nitrites and stuff like that.
Okay, so what is the pH of the nitrite?
Well, I just mentioned it was for paddings, it was around pH 8.
But for
Now,
just the one simple potassium nitrite solution.
Basically, I don't know exactly what it is, but when we do it, is not. If you take potassium nitrite or nitrate and you put in solution, you are not gonna get a pH 1 or 2 or 3. My guess is gonna be around 5, 6, something like that. Okay.
So it's safe.
Yeah, and the other thing you can do, if you have a litmus paper, you can add a little more base, which could be sodium hydroxide, dilute, or potassium if you don't want to mix cations, which I don't think the cations in that range make any difference. If you monitor your concentrations in molar, not by percent weight, then you can control it. You can switch from one salt to another, and hopefully it doesn't make a difference. And the pH, you can adjust it yourself by if it is too acidic, if you measure it. But look, pH 5 is still fine.
Good.
Okay, you're not going to be worrying too much about that. What I would worry about is if you keep putting it on top and you make excess of salt that you retain it into the structure as a salt that hasn't reacted. When the salt reacts with the surface, you have reagent A reacts with the reagent B. One of them consumes itself. If the oxidant with the salt you put in consumes itself by reacting eventually with the wood, with the cellulose, with the lignin, and you want to react a little more because you still have some potential into the wood itself to get reacted, you can add a little more. But if you add now too much of it, you are going to get it unreacted. If you leave it unreacted in the wood, over time it's going to start reacting by the decompositions that Adam already pointed out to that. So,
okay.
But I'd like, in relation to this, I want to make another observation. When you do the oxidation of the wood, you actually destroy something into the wood. And the proof of that is you take a piece of, after you've done your nitration, you get a beautiful, very dark color. Some people want it very dark. I think that's not, and I don't think that's what I want. Very dark. You take a piece of paper and wipe it over the piece of wood. You're going to look at the paper, and now the paper is orange. That orange thing is a matter, which is dusted. It's a dust formed from the wood surface, the composition components of the wood. Optically, you do not want to leave that into the wood because you might as well sand. When you finish the wood preparation, you use a scraper. You don't want sanding because you don't want those wood dust into the pores, which will affect the reflection of light from the wood. The same thing, you do not want to leave that decomposed wood into the wood too much because it's going to affect your reflectivity from the wood when you varnish it. The light has to go in, the light has to come out for you to see a three-dimensional, effect of three-dimensional ground. The reflection, if you just flood it or if you flood everything around with something like dust, so you need to address that. Now that I started thinking, okay, I still want to use the nitrite. I know it's going to make that powder. I know that powder is going to be bad for the reflectivity eventually of the surface of the wood. How can I get rid of it? Well, you could wash it, but I don't want to use water. So what I would basically could do, use some Gamsol. Wipe it off with Gamsol. Put I don't know, vacuum it up if you can. Suck it up, the powder, and then wipe it first before you go to the varnishing. Wipe it, wash it with Gamsol. Paper towel with Gamsol into it to try to remove the physical leftovers into the wood. And some of the micrographs that Adam showed, they have particles in that wood. Those shouldn't be there. For optical reasons, they shouldn't be there. If you put anything in that wood, your varnish to go there, not oil, but some varnish component to there, some resin into it, that will help. And if you look at also the system that Padding had, he had a sealer after he did all his coloration. And that sealer was a resinous type of sealer. It wasn't heavy oil stuff to go into the wood. And if you use that type of thing into the wood, it should be made of brittle resin, a resin that has been well cooked. It's brittle, gives you some color, and you can use it as a sealer. And you can use it, if you look at Brigitte Brandmeier's work, you don't want to flood the pores. Let's talk about the maple. You want the pores open. You do not want to put a layer of casing or a layer of X or something that floods everything and makes you a nice surface, which is just a surface, is not inside the wood. The Brigitte's work shows basically that you have to have some of your varnish components going into the wood there. Her sketches, layering the sketches, show that quite clear, and her micrographs actually show that clearly. And since I'm on a roll now, before I retire, I would say people look at the Brandmeier work and they found protein analysis of protein as a chemical, as a compound is very sensitive. I mean, you can find a few more, let's say exaggerate, a few molecules of protein, casein, egg, or anything else that they speculate about. And you're gonna see it's like a forensic, whatever, when the crime is committed, you find a few molecules of this. It's very sensitive to that. So violin makers look at the data there and interpret it. Oh, well, we have casein. Oh, well, we have protein. Therefore, we're going to apply it as a continuous layer. If you look at her micrographs and her interpretation, nowhere you can see a continuous layer. You can see a continuous layer of this, continuous layer of that, then the wood and something in the wood. But you never see in her micrographs or her sketches a continuous, deliberately applied layer of protein, casein. And again, I do remember the good work that was done in Cambridge many years ago. They found minerals, and the violin maker, and even now you find minerals everywhere. And the interpretation of a violin maker of what they saw was you're going to shove into the pores solid minerals, like a concrete surface. I've done all that stuff myself. I did collaborate, I mean, not collaborate, communicate with Rubio, who was doing in situ cementation of that. I tried that thing too. It's not, you get beautiful results by a variety of different systems that you use. You can have very happy clients, you can sell your violins very well. But if your intent is really to put next a beautiful copy of, today there are some people who do antique copies who are absolute piece of art, fantastic. But then you put it next to the original one, it's not going to look the same. You're going to see the differences. Anyway, violin making, the reason that I keep going and I'm passionate and obsessed with violin making is because I can't get an answer to it, a final answer. If I had the answer to everything, including acoustics and physical and looks and stuff, well, you could make them commercially, sell them. Chinese will make them by the millions and sell them in Walmart for $100. So now I can play this one, I can play that one. The point is, every time we make a violin, I believe you do the same thing, is the excitement, the anticipation of, well, okay, I put it together, I draw the first bow on it, what did I get? And of course, when you make the looks, again, you need to find something that pleases you and the customers. It's very complex, it's, keep going. I mean, it's an exciting thing to do. If I had, at this point in my life, if I didn't have this violin making, I would drive crazy doing what? Watch TV, watch the news of the day. That would be depressing, but anyway. So
That's Alcus's main big message for you, Adam. Keep on going.
Keep on going. It's exciting, and
Yep.
as long as you, well, I don't believe we're gonna have, at least in my lifetime, which is whatever it is that you're gonna find all these answers to all these questions. And from my perspective, I'm happy I don't, because I want the excitement of the unknown, the search. That is the excitement of this all. But again, at one point, you're going to find out, you're going to sort out what's important to keep going, what direction, and what's really not the right direction to keep putting effort and work to keep doing things that will lead you to nowhere. And the great deals of work that has been done in the past, I appreciate it has been done. I learned from it. But there is a point where you need to know, well, that's not the right direction to go. I'm not. This doesn't refer to what you are doing, Adam. I'm not talking to what you did. That statement is a general statement. Looking in the mirror myself, I've done all sorts of things. I've done all sorts of wood treatments. I've done all sorts of making varnish and this and that. And the other thing that I'd like to mention for whoever wants to hear my philosophy is assuming you have reasonably conventional materials like varnishes and treatments and stuff like that, colors, whatever colors. The difference is not so much in the materials. It's, oh, I have a varnish. This varnish is beautiful. I'm going to apply it in layers and I get something. The trick is the application. Most of it is basically the application. It's the vision you have, what you want to look like. Okay, so if you want to look like the antique, well, that's your vision. If you want a straight, well, that's the vision. You have materials, think about them as a palette. I do not apply layers, brushing one over the other with the same type of jar. I have a jar of varnish, is going to do everything, and then I'm going to decide I'm going to put some color into it. That could be what? Pigment, rosinates, colored oils, whatever. Those are a palette for you to paint a picture. I should have done that. Well, I didn't learn. I learned as I learn as I go. I'm still learning. But originally, I was painting. I got the varnish. I bought this varnish and that varnish and that, and I was never happy because I applied layers of varnish. Thick varnish, thin varnish, alcohol, well, never did alcohol varnish. Apply them sequentially and see what happens. But to me, that didn't work. Now I'm looking at it, I have materials. I apply to the wood, I get feedback every single step that I do. I look at the feedback I get from the wood, and it tells me which direction to go visually. And I can mix this color, that color, this the material. It's a palette, it's a painting. It's an artist painting, not a wall painting.
So I don't want to leave people with a sense that any of that the complexities of the chemistry, which are obviously immense, have anything to do with the workability of this product. I think it's a very useful product. As I understand, Adam, it's from what you found, it's stable over the long time. It's not going to hurt the wood. It penetrates very little. So let's just leave it at that and invite makers to use it. I don't, as far as potential acoustical effects, I think it's vanishingly small, if any. I've never found that the tap tones or the mass changes after tanning the wood, after doing all sorts of things. So it's so easy, especially when you're a young maker, to get paralyzed by these worries. Many of them imagine because we don't know something doesn't mean we shouldn't be doing it. I think anyway, enough said.
Yeah. So Joseph, one of my questions for us non-violin makers is what is the percentage? How widely is potassium nitrate used as a wood treatment?
I don't know. I started using after I found it was just quicker and more effective, and I know a sizable population used it. I remember Jeff Holmes, who's a dealer, saying he could just recognize a violin that'd be treated that way from the color of the ground. I don't believe him, but I believe he could be fooled because I don't think it's that distinctive. It can be used many different ways. But for someone like that to say it means a lot of people were using it, is that still the case? I don't know. I would guess it's widely used, but
I mean,
Joe, Joe, from my experience, I think many people use it. Many people use it. And as I said earlier, when I started my comment, it's fortunate that it doesn't penetrate much. So you get the color that you want. It is safe for that reason. And I fully agree with you that doesn't do any change to the acoustical properties when it penetrates 0.3 millimeters. Now,
I'm so glad to hear that.
Well, that's my experience too. And also theoretically, it shouldn't make much of a difference because you have very little oxidation or penetration on the top. What makes the difference acoustic is basically what you do with when you start your after this treatment, what you do after that. And from some study that I remember, Cat Acoustical Society many years ago, there were studies somewhere that people were doing the effect of varnishing on the tap tones and things like that. And if I remember correctly, actually the ground, whatever we call it, ground has most of the effect. The curve goes up. After that, anything you do doesn't have much effect on stiffness tap tones, other than you add more weight to it and you just move the amplitudes probably, but not so much shifting the frequencies. The stiffness is affected probably with what you do to begin with. I mean, the first steps you do after.
Why would it be effective at all? We're not putting anything on the wood that has a tensile strength anywhere near that of the wood. It stiffens it across the grain a little bit because the wood's weak and it can sometimes penetrate enough to kind of add a bit. And indeed, the tap tones do go up a little bit, mode 2. But the notion that we're doing something acoustical with varnishes seems to me very outdated.
Well, I remember Norm Pickering was talking about many years ago when I met him at Auburn. He was talking about the surface effect, and I think Jim Ham mentioned something in that direction, that very much on the bending is the very much surface, not so much the material. Norm Pickering was talking about making an analogy to those structures, honeycomb structures, which are very light but very strong. You've seen them, aluminum sheets on both sides. Then you have a honeycomb in between. They provide a great deal of stiffness, but not weight.
But we're not dealing with a honeycomb. We're dealing with a more or less homogeneous thing. Putting something on one surface simply isn't going to do much. And just from experience, I've used grounds, everything. I've started with like an oil, like liquin. It's an alkyd oil, which dries. I used that for years. It's fine. I've revarnished using other things. I've used almost any imaginable combination of varnishes, stripped them and done others, and it simply doesn't affect the sound very much. Everything has some effect. Just taking the strings off and taking the top off is an effect, but I think it's wildly misleading to direct makers to trying to control the acoustics with anything we do after we close the box, except setting it up, and that's vastly important. Anyway, that's my opinion.
Well, I'm not talking about the closing the box. I'm talking about if you have the free plates and you do a treatment on the surface, those tones will be affected one way or another. And it could be the transverse, the mode 2 or mode 5, which is the transverse versus the longitudinal. And that I've observed. And it depends. Now, if you put an oily material, including liquid, and you put that is softer. But if you put a brittle resin into it, you're going to affect it a little more positive.
Why more positively? We don't know what damping we're trying to get. This is just.
Well, damping, I don't know the damping, but I'm talking about the stiffness. That makes a difference.
Well, the stiffness isn't affected by brittleness.
Well,
I would.
okay.
Okay, we should do I mean, we should almost do
Yeah, that's another type. But more relevant, Algus, do you have a sense of what percentage of bow makers use potassium nitrate? Most of them?
I don't know, but
Some?
I think they may use nitric. I don't know, nitric acid. I wouldn't use. You can use nitric acid to color the boxwood pegs because they are not critical. I mean, it doesn't matter.
Right.
You cannot use that on a 3 mm piece of wood and use nitric acid. And I know that exactly because some years ago we had a violin. We experimented with it. We concentrated nitric acid on it, and we destroyed it. And the other thing the same thing when Fulton came up with the idea with the Tesla coils and making ozone. By the way, the ozone doesn't do much to the wood. The ozone reacts with nitrogen, makes nitrous oxides and nitric oxide. With humidity, makes nitric acid onto the wood. And if you keep it there for a week, you burn the wood. And there are people who made it, and I did that too. You made it, and after a while, you put the wood together, and the thing collapses. It disintegrates. So nitric acid is bad. You can use it, and I do use it for coloration of the pegs with moderation, everything. But you shouldn't use that as such unless you think you can control the penetration. You think you can control the concentrations, which most of the violin makers, they don't. They look at the recipe, they apply something on it. I'm not sure how deep, the old-time violin makers can actually control all these parameters, or they understand what they need to control. Some of the parameters we don't even know what we need to control.
Yeah.
Same in the acoustics. So we don't know everything about it. And I do hope I can learn more.
Yeah. So, Joseph.
But Joe, I basically I agree with you. I'm not contradicting anything I think that you said.
All right.
Okay. Are there any final questions? If they're not, thank you, Adam, for this fascinating presentation and led to a lot of
Many thanks,
interesting